of SSSEC channel. In this episode, I want to talk about data dependency, and I want to talk about why data dependency is important and why it is useful and how we can get this information from a binary code. So the prerequisites of this tutorial is the introduction, is the video of introduction to P-code intermediate representation. And if you haven't already watched my video, please watch it first. I put a link to that video here in this slide. Okay, let's start by talking about what is data dependency. Data dependency refers to a situation in a program in which an instruction depends on the value and on the data produced by another instruction. For example, in this simple example, in the first line, we assign the value 5 to variable A, and in the next instruction, we use variable A to calculate variable B. So because the calculation of variable B depends on the calculation of variable A, we say that these two instructions or these two code lines are dependent to each other. Now, why data dependency is important? Data dependency is important because of program correctness, because it preserves the correct order of dependent instructions that ensures the computations yield the right results. Also, it is important for security purposes. Data dependency can help us to identify vulnerabilities much faster. And it shows like how the inputs into a program actually propagates. So here in this example, I have a very simple function which is vulnerable to stack-based buffer overflow. Here you can see that I have a function and a function argument, and this user input was copied to a buffer using strcpy without checking, without any validation or without checking the length of the buffer, and that caused the buffer overflow. So by tracking this variable user input, we can see which lines of code are relevant to the vulnerability, and we can filter out those lines of code that are relevant to vulnerability detection. That's why we say like data dependency can be helpful for security purposes, for reverse engineering, because we can understand like how data in the program actually flows. Okay, here in this slide, I have two examples that shows the data flows at binary level. At the left side, we have two assembly instructions that in the first instruction, we copy value 0 into register R6. And in the next instruction, we read that register and copy it to register RDX. So in the first instruction, we have write to register, and in the second instruction, we have read from that register. Because between line 1 and line 2, there is no other instruction that manipulates and modifies the value of RCX, we can say that the value we have here in line 1 is the same value in line 2. So line 1 and line 2 are data dependent to each other. At the right side, I have a simple assembly instructions that you can see. In the first line, we have write to memory. So we move value 2 into the location and into the address that RBP minus 0x20 is pointing to. So we have a location and we copied value 2 in that location into that address. In the next instruction, we read from that memory. And because in line 2 and in line 1 and in line 2, there is no other instruction to manipulate or modify, the value inside RBP minus 0x20, we can say that line 1 and line 2 are data dependent because it's the same, actually it's the same data that we are writing to and we are reading from. But what about line 4? In line 4, we cannot say that the data that we write in line 1 is the same data that we are reading in line 4. And the reason here is that we have a callee function. In line 3, we call a function x, whatever, and we really don't know what happens into this callee function. We really don't know if f callee modifies the value inside RBP minus 0x20. If this function modifies the value inside this location, then when we read RBP minus 0x20, it's not the same value that we write in the first line. So because f callee can modify the value inside this location, then we cannot guarantee the value that we read here is the same value that we write here. So that's why we say there is no data dependency in line 1 and in line 4. Okay, now what is data dependency graph? Like control flow graph, like control dependency graph, data dependency graph is another program graph that helps to analyze the program. Data dependency graph is a directed graph in which each node is a variable and the edges shows and represents the dependencies between these variables. So here in this slide, I put an example of data dependency in Ghidra. At the binary level, data dependency comes on top of P-code, on top of intermediate representation. In Ghidra specifically, it uses P-code IR, and the data dependency comes on top of P-code statements. So that's why I'm insisting on watching my previous video, because you first need to understand what is intermediate representation, what is P-code, how it is look like, and how we can generate that in Ghidra. So please watch the previous video if you haven't watched it already. Now I have some P-code IRs in this example, and you can see that register 0x20 exists in multiple IR statements. And this redundancy shows a data flow between these P-code IRs. In the next slide, I tried to actually create a sort of a graph, part of it, to show how it can look like. So I have register 0x20, and you can see that, in this graph, each node is a var node. It can be var node or operations. It can be operations, it can be var nodes or constant variables. And you can see that this register has been used in multiple P-code statements. And that's why there is actually an edge between these nodes. So in Ghidra, the data dependency and the P-code IR look like this. But in another tool, for example, in Anger, Anger's data dependency also comes on top of Vex IR, and I try to cover it in future videos, but it can look like different than what you are already seen here. But I hope that this video was useful for you. If you have any questions about data dependency, feel free to leave a comment in this video, and thanks for watching it.